let me go ahead and switch over. I'm just gonna drag this over. Okay, cool. So yeah, our next step then is really to talk about linear regression. So linear regression, we're going to talk about, it's going to be a little bit more fluid than being like, oh, this is section 18, this is section 19, this is section 20. And this is really what you'll be using for your project, for this Mod 2 project, is basically to use linear regression to make predictions. So it's good to kind of go through like a little bit of like how do we do this. So I'm actually going to kind of go back a little bit to covariance and correlation. You guys remember covariance, correlation? It's not familiar? Okay, I won't go take too long with it. But the main thing with covariance basically is got in their name, variance, right? Well, variance was basically saying how well or how spread out are we from the average, right? The mean, right? And so we had this sigma squared and we had this equation, right? Basically, how far are we from the mean, and we do a square. Anyone have an idea why we square it? Like, why don't we just do like x minus b without the square?
Yeah, because we want an absolute value. We don't want to deal with negatives.
Yeah, we don't want negatives, because the problem is like if you have something that is, let's say like the mean is at 0 and you have something that's -1 and then negative or +1, those would basically cancel out and you would have a variance of 0, where clearly that's not true. Where if we squared it, we would have, say, it's 1 off from the mean squared, and then 1 off from the mean in the negative direction squared, and you get a positive number. Note that there's other ways to measure this, like essentially variance, though this is a much more common way. There's a kind of a few reasons why. This is usually called the L2 norm. If you wanted an L1 norm, you can actually use the absolute value. So they would describe the same thing, but in general in statistics, we have traditionally gone with sigma squared. So just know if someone talks variance, this is the way we're measuring it. But covariance then is actually not that hard then. It's basically saying, okay, we do the same thing, but we consider it between two variables. Basically, how well are these like essentially correlated with each other? So saying like, how do they change from each other? So we have x minus, or each point in x minus the average in x times the y minus average in y. So that way we kind of like also have that connection between the two. So one thing to note, and also note that usually we represent it with the sigma, but with the xy underneath. Okay, so this kind of represent, you can kind of see hopefully the similarities between these 2 points, right? So one thing to note though about covariance, which I don't know if we really talked about it, is that basically positive covariance means that these things are very like close together. Like they have a strong connection between each other. If you increase x, you should also expect y to be increased too, at least, with the pattern that we see. Negative covariance, right? So a negative number means that they correlate in the opposite direction. So if we increase x, we would expect y to be decreased, right? As we kind of move across there. So that's kind of like the idea here. But one thing to note is that the range is from -infinity to infinity, right? So it's kind of tough with covariance to be like exactly what level, like how, like if I got a covariance of like 5.2 versus like 6, are those more correlated by how much exactly? And it's not as easy to compare it because of these negatives in the scale of what we're doing. So one solution to this is using correlation. And this is where we talked about Pearson's correlation factor. And you can see if you look at it in this way, Pearson's correlation would usually represent with little r, and covariance right here, you can see the similarities pretty quickly, right? Like the big thing about it though is that basically this is independent of units. You can see that basically there's no units that are kept behind. Remember that n is basically just representing how many there are. But in this case right here, we actually are getting rid of the units completely. And so this is just one way to do correlation. There's other ways to do correlation as well. One thing is eta, for example, can commonly be used too, though I know the curriculum doesn't mention about it. And eta, if you guys ever look for it, it's like an n. It looks like an n, but that's kind of like funky looking n. So eta is another way to calculate it. It's a little bit different, but the same idea. And what's nice about this is that we're independent of units, so we don't have to worry about what the scaling of each x and y is. We don't care about if it's dollars, if it's number of bunnies, it doesn't really care. And then what's nice too is that it's normalized. So it's normalized across -1 and 1. So again, negative correlation, positive correlation, we can still do that interpretation, but now we're restricted to -1 and 1. And that makes it a lot easier to compare the correlations. Okay, sound good? Any questions on this so far? Cool, all right, hopefully it's more or less for you. So now you can kind of see a little bit, if you use like Pearson's correlation, a very high 1, right? It's basically perfect correlation, right? Basically, as you increase X, Y will also increase in the same amount, right? And then we see 0.9 is like, well, in general, it tends to increase, but not necessarily every single time. And so as we kind of go down that scale closer to zero, zero meaning no correlation, basically, it's completely random from each other. It's completely independent from each other. And then we have like negative correlation where basically as you increase one, the other one goes down. Note that this correlation does not necessarily mean that they cause each other, right? It just means that they are related in this way. It's like if you look at a higher value of X, you expect a higher value in Y, but it doesn't necessarily mean that you're changing X to change Y. And though we will try usually to interpret that way, you have to be aware that it's not technically giving that purpose, right? It's just saying they are related in some form or fashion. Okay, cool. So the reason why I'm showing this is this is basically the core idea of linear regression, is that what we want to do is basically say, well, okay, if we know what X is, or we know a bunch of features, can we predict some other target variable? Like, can we say like, well, if we know these things are true, for example, going back to like the weight and height, for example, let's say weight is our target variable, the one that we want to know. It's like, well, if we know their height, if we know how old they are, if we know their diet, if we know like a whole bunch of features about them, could we predict, you know, could we make a good guess on their weight, right, would be their target. And so that's the idea of essentially what we call statistical learning. And this is where I will say is like, depending who you talk to, they'll call it statistical learning. Some people will also call it like machine learning. And I would actually kind of go on the end, like it really is machine learning. So if you guys have been hearing like that term and stuff like that, it's just that typically like linear regression is so like, what's it called? Like it's so well used. It's so like, I wouldn't say old, like it sounds weird to say like it's old, but like it's just been well developed and stuff that people don't even think about as machine learning, but it really is. Like it's a type of machine learning part. But sometimes you'll usually hear people talk about as statistical learning. And we'll talk about like what that learning is in the future. But some intro, right? Well, okay, I kind of just give an example, right? Is that you have different variables, right? You have an independent variable, a dependent variable, and a controlled variable. And basically a statistical model, right, is basically just some function that's going to map what defines that relationship. So you have different variables essentially. It's like, well, if we have these different parts in here, could we then predict what the actual like target is, you know, what we might call as the dependent variable. Controlled variable, I threw it in there just because it's kind of useful to talk about. Is controlled variable basically it's like, oh, we keep this constant. So let's say, for example, we're looking at like for weight and then like looking at height, maybe you keep the age constant. So it's a controlled variable. So you're only looking at people who are like age like 30 years old or something like that. And that would be a control part. So it wouldn't be part of your model, but it's an assumption of your model. Okay. And later on, when we do multiple linear regression, which really just linear regression, but multiple times, is that we can actually think of the controlled variables as their own feature. So we can slide the ages around and stuff like that and imagine taking slices of like saying, well, what about 30 years old? What about 40 years old? What about 50 years old? That's kind of like what multiple linear regression really is. Okay, cool. So some processes and terms, you'll hear me kind of use these things, so it's kind of useful to review, and you'll hear them a lot as we get into more machine learning too, is one is called the parameters. So parameters are basically the things we use to tune, like not tune the model, but like the parameters are the things that basically describe the model. Like, so for a linear regression, linear meaning line, we're gonna have a line. And so you can draw many different kinds of lines in mathematics, right? An infinite number of lines. And we can adjust the parameters to make different kinds of lines. So in general, what we're gonna do, we're gonna adjust the parameters of a linear regression model until it fits as well as it can to, you know, our data itself. Okay. And then we have our features and our target. So our features basically are the things that we think of, like the things we, in a sense, have control over, or things that are like, we do these things and it's gonna make a change in some target variable. So with my like weight analogy, weight would be the target, right? And height would be a feature, and then other parts would be a feature. But note that like, there's not like a real reason why you couldn't say like height is the target, right? And then adjust the weight and stuff like that. But in general, we try to think of the target being like, is caused in some form or fashion by the features themselves, even though that's not technically always true and not even necessary to be true, that there isn't like, we can use correlation without causation, but still do a good job predicting things. So just kind of be aware of that difference. But in general, the target is the thing we're interested in, the thing that we want to know about. We want to predict it. And our features are the things that we can kind of measure and make predictions off of for the target. Anyone got me so far? Yeah? Cool. All right. So one thing I'm going to talk about really quickly, just model validation. I know that's technically, I think, in section 19, but it's important to know about like how this works. This is where like I saw statistical learning or machine learning. It's basically, it's the way you learn. So how to say this? If you're a kid, right, studying for a test, right, the teacher is probably not going to just give you the test, right, and say, here's the test, I won't give you the answers, or maybe they do give you the answers, right? They give you the test and say, all right, go ahead and study this, right? And then, you know, in a month, you know, we'll have our test, and it's the same exact test. Obviously, you guys are like, yeah, that's a bad idea, right? Like, there's a whole bunch of reasons why. And the main reason is that basically, there's nothing really stopping the student figuring out the answer and then just memorizing that answer for the test. And literally, like, let's say it's a multiple choice test and it's the same exact order, they can literally keep their eyes closed and just mark A, B, A, C, B, D, whatever, right? Like, they don't actually have to learn anything, right? They can just memorize stuff, which arguably is not really learning. Same thing happens with our model, is that if we just give it all the data and we say, what's the best linear model you can put on this data? And it can figure this out. It can figure out the best thing it can do. And we'll talk about in the future about how it does this. But just trust me now, you can figure out the best way to fit this model. The problem is that you don't actually know if you are essentially learning from the real data or you're just memorizing on top of this data. So it's kind of similar to what Alvaro was talking about with overfitting, is that there's an issue with this where you basically are just memorizing the answers and don't really have a way to generalize to the rest of the population, the rest of the data set that your data was coming from, right? So we can do something called validation. And validation is a strategy essentially to say, well, we don't know, we don't have all of the population data. We don't have an ultimate test at the very end. So what you can do instead is you can split your data into like, okay, this is my training data. This is the data that I'm gonna like study, you know, my practice test, you know, we call it the training, right? And then at the end of it, we can test and see how well we perform. And the goal here is that we can say, okay, we split the data. Usually it's like an 80%, you know, for training, 20% for testing. Don't worry about those numbers. We're going to talk about those in the future too. But the idea there is that we keep part of this 80%. We look at just this and we never look at the testing thing. And we basically take this training data and we look at it and we study it. You know, when we say we, we're talking about linear model, and you do the best you can to fit on this data. And then you say, okay, here's the model. All right, here's what I like design this line. And then you say, all right, how well does it fit on this testing data that it's never seen before? And hopefully, if the testing and training has come from the same population and you generalize really well, you should hopefully have a good result still on the testing data. Will it be the best result? Definitely not, right? Like, you probably won't have the best result, but that's okay, because you're okay to get a little bit wrong if you can generalize better. Because we could technically try to train on the whole data set, but it'll just be memorizing all the answers. Okay, does that make sense? Yeah, Jessica, you have a question.
Do people ever like run kind of iterations randomly separating 80-20 and running models and then comparing those?
Mm-hmm. Yeah, so that would be exactly, you do a split train test split, as we call it. And then there's even a better strategy, because then the problem people say is like, well, we have 20% data we never use to train. Like, that would be really nice to use, right? Like, that would be kind of good to study off of it. There's a strategy called cross-validation, which we'll talk about. And cross-validation basically says you strategically basically take 80% of the data and train off of that. 20% is testing. And then you train off of it, see how well you do with the testing thing. And then you do a different split where now you have a different set of 80% training. And basically you take all of those models together and combine them in such a way that you hopefully then aren't overfitting on the testing. Like, you're not overfitting on your training, like your full data set, if that makes sense. And with that full data set, you're going to get a little more general because you're trying out different things each time. Like, hopefully that kind of makes sense. Like, I'm doing this very quickly. Okay.
Yeah,
so,
it makes sense.
Yeah, it's like if you take it and you divide it in 5, and then you say, well, I'm going to train on these 4. I'll validate with the 5th. Then the 5th becomes part of the next 4, and you pull another one out until you've gone through all of them, basically. You know, using all the combinations.
Yeah, that's basically it right there. is that like take this full data set, pretend this is all your data set right here. And I'll get into semantics a little bit. There's something to note is that technically you still have like a last data set, which is your true testing set, because you still want something that you've never seen before in the end. But essentially just look at this stuff. And it's like, okay, well, the first round, I'm just going to train off of A and B and then test with C. And then the second round, say, well, let's try with A and C, train with that stuff, but test with B. And then with B and C, train with that and test with C. And then look at all of these models together. And this is basically what cross-validation is. And then you would have this guy right here, like your super model, okay? And you would basically compare these two, which is a set you've never seen before. So you can kind of going a little bit, we'll talk about this in the future, but this is usually called, this is your training set in your cross-validation, this is your train. This, and this is where I like to make a very distinction, is that this is usually called your validation set. So like you're validating your training essentially. It's also sometimes called the dev test or dev set. And that right there, you use the train and your validation together to basically get a better idea. And then when you're all done with this, then you finally go ahead and you test against your test set, which should be something, your test set should be something you've never seen before. You can think of this as new data, or you could split up at the very beginning to make sure that's never been seen. But ultimately, you still would do something like this. This would be cross-validation, which will help you go across stuff. Because in the end, if you use just this and like never like test it against data you've never seen before, this right here, like there's always going to be biased, right? You're still going to see everything. It's going to be less likely, but you're still going to have issues where you're never going to know. It's like, well, did this generalize really well? And that's why you always have to have this test set at the very end. We can talk more about this for sure, because we're going to talk about it in like multiple linear regression and talk about like cross-validation. But this is where you guys know Kaggle, right? Kaggle competitions, kaggle.com, Kaggle. What they'll do, they'll give you this data set. And then they'll have this data that they never show anyone. They might not even show at the very end. And this is their test set. And then you have this stuff. And the problem is like, well, this is all the data you have. Well, if you split this off and only train off of A and B, you're never going to see C. So you can do cross-validation, for example. So you can use the whole data set, but still get ideas like, well, you're generalizing really well, but you won't ever know until you finally test it against the data set that you've never seen before. That's kind of like what Kaggle does. Okay.
Cool. Great.
All right.
Thanks.
No problem. And yeah, I just want to put that because it is an important aspect. All right, and then last thing is those loss functions. Like, how do you know how well your model's doing it? It's called your loss function. And this thing basically is evaluating your model compared to the data. Note that these terms, feature, targets, parameters, validation, loss function, these are all based on statistical learning and machine learning in general. It's not just linear regression. This will extend outward to other models too. But you can think of it in these terms. Okay, cool. All right, and note that for linear regression, loss function is going to be the MSE, the mean squared error. All right, so here we have our linear regression. Basically, it's a line straight to some data points. Cool, right? So I'm going to kind of go through this. We have 15 minutes. We can go pretty quickly. It's basically a way to model the data science, model the data. And I like to say linear regression is a really good data science go-to. Everyone talks about all these like really amazing machine learning models that are super fancy and super cool, really cool. A lot of times all you need is linear regression and it works perfectly fine. And linear regression is well known. You can explore it really well. It's also something that's explainability of the linear regression model is a lot easier than some other machine learning models, which are described more like black boxes, where it's a little bit harder to know exactly how the model came up to these results. Linear regression, you tend to actually, because you essentially have to define the model for it and then tell it to fit against it. It's a lot easier to interpret like how this model works. So interpretability is really powerful with linear regression. So it's a good go-to because it's quick and easy, and sometimes that's all you need. All right. So creating a linear regression. So I love this little diagram here, because if you look at this, and I'm not saying, so you have to know it right now, but if you know how to like look at this thing and you can understand each part and you can explain each part, you know linear regression. Like you will pass every interview question if anyone ever asks you about linear regression in general, like, because this is all you really need to know. And so I'm gonna kind of break this down a little bit, but I think it's kind of good to kind of talk about. So these green squares, those are your data, right? So those are your data points. Your blue line right here, that's the model, linear regression line. Your Y, that's your, you can hear your response variable, you can think your target, right? X is your explanatory variable. This is more on the science terms, but we're gonna think more data science, is your features, right? Or a feature, right? And so you can basically look at your features and your data point has some value in Y, right? And you say, okay, how was it formed? And then we draw a line essentially through these data points. How exactly we do that? We don't worry about that right now. Basically, the computer figures out how to minimize the error, basically how close these data points are. And then what we do, say, well, how do we measure that error? How do we know how well our model does? What we can do is we say, okay, how far in Y, in this Y direction, how far are we off from our prediction? So the way you can kind of imagine this, so this is like visually going through, but you kind of imagine this is that if I have, let me get something that's going to be readable. Let's say I have this data point right here. Oops, gotta annotate. There we go. I have this data point right here. And I say, okay, this data point, I'm just gonna make up a number, is like 30 on Y, right? And so the X explanatory variable, doesn't really matter what this variable is like 2, okay? So when the value was 2, the data point was actually 30, okay? But our model is slightly underperforming that. It's like says, oh, it's 25. These numbers are not to scale, I'm just kind of making things up, right? But you can say, okay, the model says when the value is 2, it should be 25, right? So that means the difference in this part is going to be 5. Okay, so we're off by 5. Make sense? So what we can say is like, well, okay, like on this case right here, you might say we're off by -2. Right, so these are all the errors. We can collect all those different errors. So we're off by 5, off by -2, off by -10, whatnot. If we just added them up together, we have the same issue we did with variance, right? Is that now those positive negatives could add up and sum up to 0. So what can we do instead of just adding up all the errors together?
Square them.
Square them, perfect, right? So then we have something that's actually going to be like positive. Also, what's nice about squaring it as well is that we actually can punish larger values. So if we're really far off, like let's say we're off by like 20, right? Well, that error is not just gonna be 20, it's gonna be 20 squared. So equivalent to 40, right? Versus like off by 5, if we square this, right, that's 25, right? This is almost like a little bit under twice as much as this error, but we can see that it's actually 4 times as much over from here. So you can kind of see that difference that we basically have a different scaling for how we count errors, okay? So that's another reason why we square it as well. But the way we say this, like, okay, you can also see this weird Y hat minus Y. We usually call the model itself Y hat, okay? And Y hat basically is our model, our prediction, right? This is how we predict it. The Y value is just saying the actual data points themselves. So we can say the error, it's just the sum of all of these predictions minus the actual data squared. Okay, and so you'll see here is that what we call this is our MSE, our mean squared error. It's like, well, where's this mean coming from? Well, that's because we're basically going from here. Now, one thing to note is that our mean squared also, for R squared, we're actually going to compare it with the worst possible model. Did anyone got the worst, like, what's the worst model we could use? That's a tough one, right?
An inverted line of that?
Maybe like an invert, yeah. Yeah, that's kind of a good one. It's one of those things like, oh, it's like, is that really the worst model? It's like, yeah, maybe, right? I should say like, it's not really the worst, like when we say the worst model too.
Could it be the slope is 0 and the intercept is 0?
Yeah, that's getting closer to it, right? And I would say probably Carl's is probably like actually the worst. Like he's like, let me actively try to like do the opposite of this. But when you usually say the worst possible model, it's like, well, what's the lazy model? That's kind of like the better word for it. And the lazy model is you just say, what's the average? Like if you wanted to predict, you know, how heavy someone is in the US, you can just, let me make this real quick. We can actually, use just the average to say, well, whatever the average is. And so you can kind of think of it as a straight line straight through the average. And so that's kind of like what we'll compare our model with, to say, well, did it do better than this? And if you didn't do very well, then that means your model's not very good, because you basically just took the average. You might as well just have said the average. This is basically taking the difference from here and the difference from here is going to give us our R squared. Okay, does that make sense to people? Okay, and if you think about this really quickly with like back to ANOVA, what we talked about last time, right? What we did, we had our model was essentially saying, well, is there a difference in our data points, like the average in the data points versus the whole average? That's kind of what's going on here, except our model is not individual categories. It's actually this full line right here. And remember how we compared this guy, basically the average of all the data points versus the averages for each group. Basically, our model says, well, the averages in each group, or the groups matter, essentially. That's what we were doing with ANOVA. And so that's essentially what's going on here. And that's where that connection between ANOVA and linear regression, they're basically the same thing, except that with ANOVA in particular, we're just considering these as separate categories versus as a spectrum over here. Cool. That kind of more or less kind of gel together. How are we doing? Thumbs up, thumbs down, sideways. Okay, cool. I like to give you guys context first before we dive into any deep math stuff, because it's kind of good to say, like, where does this all come from? So this is where I kind of say, okay, we can compare it with, is it any good? So you can see here is like our worst model, which really should be called the lazy model. It's like if you weren't going to do any work. And so you can see here is that basically we say, okay, like, well, how far in this orange, this is from the curriculum, by the way, you can see how quickly, it's like from here, this orange, how far are we from this data point, from this average? And then you say, well, how far are we data point from the actual model here? And then how far is that model from the actual like lazy / worst model? Okay. And we basically take all that information together and we can form basically a metric to say, well, okay, it's this much better than, it's this much better than our lazy model. And so this is where we can talk about like, oh, like in that first question, saying, oh, like what % of the variance is explained, right? That's essentially what we're saying, that we can explain that variance better than just taking the average. And that's where if you can kind of think back to ANOVA, like it's like, oh, this is kind of making sense, like analysis of variance, right? For ANOVA, that's essentially what we're doing here, but we're doing it over a spectrum instead of like a category for each part. So I think that kind of helps a little bit tie these together, like how they're related. And this is more general in this case. In this case, these kind of models, the ANOVA linear regression, there's something called the general linear model, the GLM. So if you're curious about that in statistics, you can definitely like Google like general linear model. And there's a whole bunch of things you can talk about it. But once we know this, we're like, cool, we can then compare it with our actual worst model. I'm gonna skip this part because I kind of just repeated this over and over again. All right, so now we can say, okay, but how do we know linear regression is gonna work? So I have this part right here. I think the curriculum might have a similar graph to this. Is we have a linear regression line in red and these blue data points. And I'm just gonna ask you guys, is this a good model? Thumbs up, thumbs down, I don't know. I saw kind of like a thing that I see, oh, this is good. I'm getting a whole lot of shit. So real quick, give me a thumbs down if you're like, this is a horrible model. Okay, give me a thumbs up if you're like, it's looking pretty good. I don't know what people are talking about. Like this is looking decent, right? Like it's not the best, but yeah, I see some kind of shakes. Right? It's looking pretty good. And give me a sideways and be like, I don't know, Victor. Like just tell me the answer, right? So, all right, good. Everyone's got more or less. So I saw some thumbs up. Like obviously, it's not the best model. Could be better. Somebody give me a thumbs down and tell me why it's. What are some reasons why you say it's a bad model?
It doesn't look like a linear model to me. So I can definitely see like a curve in the data. So it doesn't look linear to me. Maybe it is. I mean, you know, we could test it and see. But yeah.
Yeah, good. So yeah, I think when you say it doesn't look linear, you're talking about the data points. It's like if you look at it, like you could definitely, like I think if you guys squint at this, you're like, yeah, I could see this. Is that we could draw a line that's closer to kind of like this curve, right? That's kind of like starts off kind of small and kind of comes up almost like kind of like a, I don't know, like a little wedge coming out versus like a straight line, right? There's another thing too in here that I don't like. And the big thing is that it does pretty decently. Like if I looked at just this guy, like I didn't know anything about outside of that box, I'd say like that doesn't look too bad. That looks kind of like what you should be. But then if I look at this box over here, you're like, man, this model got worse and worse. So our model's actually doing worse and worse as we move forward. So that's not a good sign either. And we'll talk about what that is. That's actually called heteroscedasticity, which is a mouthful. But basically it's just saying is that our model's getting worse and worse, or our model doesn't doesn't do the same prediction as we go through the different values. So we'll talk a little bit about that. But yeah, definitely one here is that it's not really linear, right? So linear models, linear regression, does not work if the data is not linear. Hence, this data point or this data set. This is not a linear model. You can try to draw a linear line through this. It's never going to be great, right? And there's actually ways we can solve this. So we can still use linear regression, but we can modify the data in such a way to basically make it into a linear regression. Or you can think this equivalent way is we can modify the linear regression to be a polynomial and fit this. And this is called polynomial regression. Okay, but we'll talk about that in the future, next week for sure. Excuse me, I'm gonna sneeze in a second. Thank you. All right. So thank you. All right. So let's check out some assumptions. So one is that it has to be linear. Like linear regression is not going to work if it's not linear, right? There's some ways we can cheat around that, but in some form or fashion it has to be linear. The other thing is normality. So one thing I'm going to say about this is that everyone just like kind of look at me for a second and like really focus in. Normality is not about the data. It's about how far off the data points are. It's the residuals. So what that means, it's not that the data is normally distributed. It's that the data points around the model itself are normally distributed. Does that make sense? So what I'm saying here is that if you kind of imagine, like, remember how we do like np.random? If you imagine like, okay, for np.random, I'm just going to generate, oops, I'm trying to draw a line. If I draw a line like straight down here, and say, generate me some data points around this like value right here. So you might get some values up here, some values up here. The values that are produced should look like a normal distribution. Does that make sense? So you should have most points clustered in some level right here, hopefully where the model is going, and then fewer and fewer points as you go out. Okay, if that's not true, so these distances from here to here, this is called the residual. So it's like the extra bit, right? The thing that the model doesn't explain, the residual itself, is that these residuals should be normally distributed. That means most residuals should be relatively small, or at least clustered around, and then should get further and like fewer and fewer. If you have, for example, let's say data that looks like this, and then a line through here, these are not normally distributed because there's kind of like two parts over here. So that's the assumption that we need to check. And the only way you can check it is by trying to make a linear regression line and then check, hey, do the residuals actually distributed normally? Does that make sense? Okay, so normality assumption for linear regression is about the residuals, not the data itself. Okay, cool. All right, and then I won't go through this whole thing. You can check normality through a few ways. One is through a QQ plot. That's very common. You can use other tests for normality. I personally think that, I don't know, maybe it's because I'm a visual person, but also I'm kind of like, it's fuzzy and stuff like this. There's different tests you can use for normality checks. I think QQ plots, or even just doing a histogram, you can see these two different histograms. You can very quickly see, is it normal? And normality assumption is something that's the easiest thing to be like it's not quite normal, but it's close enough. So that's kind of like the good thing about it. The last assumption is heteroscedasticity. So heteroscedasticity, basically, like I said, is that you're, well, I kind of mentioned like that trumpeting kind of look from this original, let me just make it smaller. This data right here, you can kind of see how it trumpets out. Your heteroscedasticity basically is that your residuals, the range of that residuals doesn't change. So at first the residuals are very, very small here, and then the residuals get bigger and bigger. And so that would be represented by something like this. So you can see if these were the plot of the actual residuals, so not the data itself, but you can think of like how much off is each data point from the model, it would look like this. Does that make sense? Okay, so yeah, again, this Y is like saying how much that error is, and this X bar is basically this x-axis here as we increase or decrease across the x-axis. Okay, so what we want is something called homeoscedasticity, right? Homoscedastic, as that's what we want right here. The residuals are evenly spread. So normally you'll see a plot like looks like this. So you can basically think this is good, like this is normally distributed, and you can actually test this out, like, you know, is it spread out? But if there's a pattern in here, like you can see there's a definite pattern as we kind of increase that x, that means your linear regression isn't quite what we expect, and we don't want this. There's ways you can fix this. Heteroscedasticity is usually the assumption that's going to mess up your linear regression. If your linear regression is going to fail, it's probably because of this guy right here, because it's deceiving at how well it works. Like you can kind of see, like, it looks like this should be good, but this is heteroscedastic. And so that's why it's important to look at the residuals itself. Okay. Cool. So with that, that was the introduction to linear regression, like how linear regression works and everything. Next time, we'll actually talk about multiple linear regression, which is basically, I'm just going to quickly say it, it's the same thing as linear regression, but like with more features. And then we're actually going to code that and say, okay, like how do we actually implement this in code of like multiple linear regression, multiple features and stuff. And we'll talk about cross-validation and all that good stuff. Okay, cool. So I know I kind of went a little bit over, but is there any questions that we, you guys might have as we kind of reach the end of this? No? All right then. Well, I'll let you guys go.
So I got a question. So
yeah,
for the project, it's mostly going to be focused on linear regression, right?
Mm-hmm.
How about all of the statistic stuff that we test and, you know, all of that good stuff?
Yeah, so that by itself is not going to be directly related to the project itself. Mm-hmm. We'll talk about like how you can check the, for example, the p-value for your feature in your linear regression. So if you remember the ANOVA table, that can be like, that's how the most, to be quite honest, you'll use the hypothesis testing with what we've learned for this section, but it won't be directly related to the full project.
Yep.
Okay, cool. Yeah. Yeah, so yeah, we'll talk maybe more about the project. If you guys are curious, you can definitely check the project out right now, but we'll definitely be talking about it over the next, you know, week or two. Okay. All right, everyone. Well, it's Thursday. I probably won't see most of you until next week. So if I don't see you tomorrow, have a great weekend.